You need oxygen if you're above 20,000 feet. So you measure the temperature and you get that value. You measure the pressure and you get this value. And then you measure the density. And you get that. So do you need oxygen? In other words, what's your altitude? We've got three different numbers here that we could read altitude off of. So you guys have your books with you? Go to appendix. There's two appendices back there. I need to look. We need the one that's English. So you're looking for Appendix B. And Appendix B lists altitude on the left, temperature, density, and pressure next to it. And so find the temperature, the pressure, and the density that I've listed here and read off the altitude. And again, in this table, we're looking at H sub G. So typically when I write H, we're just using the no, we're using just H, sorry, not the geopotential. All right, so what altitude do you read? How about for the temperature? What do you get? So we're looking at this chart. All right, so this is our standard atmosphere table. We're doing it in English units. So you're finding values, what altitude do you get? What's the H value? Somebody get a number? Look for this one. 25,000? Is that H or H sub G? That's H sub G. What does it list for H? And so there you can see the difference. So this is H assuming constant gravity, and this is the actual value that we want to use. How about somebody else? How about for that pressure? What do we get? Anybody else got a book looking this up? You shoot out a number. What are you looking at? 26,000 for H sub G. And then H is pretty close to that, right? Because it's an approximation. So what we're looking at is this section of the tables. And what do we have? We have 429, right? So we're almost at this value, but not quite. First of all, we got 25, and then when we looked up the pressure, 7.53. we're more down close to this one, right? And then the density, what do we get for that? And notice when you're looking at these tables, pay attention to the exponent, this plus 2, that means times 10 to the second power. That applies to everything below that till you get down here. So just make sure you pick up that exponent when you read the charts. Okay, density gives us 1.01. So that's down here. So we're reading about 26.5, right? So what altitude are we at? Based on standard atmosphere, we're reading 3 different values. So really, we have 3 different estimates of our altitude based on these measurements. And then this one, the top one, is what we're going to call temperature altitude. And this is called the pressure altitude, and this is called the density altitude. And those are the actual names for it. So when you're working some problems, it might say the pressure altitude is 26,000 feet. That means that you get the pressure from that altitude that they're giving you. If the problem says that the temperature altitude is 25,000 feet, then you know you have this temperature. If they just say altitude, then you read standard atmosphere for all of the values. So the temperature doesn't quite match up exactly what's in the table, so what can we do about that? Can we get a better reading? Yeah, interpolation. You guys still do that in thermodynamics? You have the steam tables and you have to interpolate. So let's do that. I'll remind you how to do an interpolation. So now we're just going to look at the values that we get in the book. So at 25,000 feet, we're going to read the temperature of 429.64. And then at 25.5, we get, this is from the table, so we just get this number. Did I copy it down right? $25.5. Yeah, okay, sorry, I was having a hard time reading across all the way up there. So I picked these two because our actual temperature is between those values, right? Yeah, okay, so gosh, I'm having a hard time thinking today. It's less than that, but greater than that one. So this is the altitude that we're trying to solve for. So if we plot these numbers, this is temperature and this is altitude. I'm going to exaggerate the difference here. These are actually closer together on the right. At this temperature, we have an altitude of 25.5. At this temperature, that's the altitude. And so the number that we're looking for, we're going to say is on that straight line between the two values. So really what we do is we say, okay, I'm going to draw an equation of the straight line between these 2 points and use that equation to calculate h sub g with this x value here. But interpolation is an easier way to do that, and in fact, all we do is equate the slopes. So the slope of this middle line here is calculated by delta y over delta x. So there's delta altitude over delta temperature. And then I set that equal to the slope of the line between the 2 points that we know. So I set that equal to 25.5 minus 25,000 over the delta temperature. And then we can solve for this. And get that number. So a straightforward way to remember this is that you're just equating slopes of the line that you don't know to the point you don't know with the slope between the 2 points that you do know. The way I learned interpolation and the way I remember it is that you take the ratio of this to this, which actually involves moving this term down here. In this equation, and moving that term up there. And this is an easier way, I think, to remember it when you're using the tables. But it totally comes from just equating the slopes. You see what we're saying? You take this and ratio it to this, and then you take this and ratio it to that. And I think when you're looking at the tables, you're looking at this column, so it's easy to grab this and then divide by that, and then grab this and divide by that. But it amounts to the same thing. You're really equating the slopes. It's just how you algebraically do it. Have you all done this before? Yes? Okay. Well, this is, if you haven't done it for a while or you've forgotten it, this is how you do it. And so in the homework that's been assigned, I will say interpolate. Some of them you just read off. I'm saying interpolate. Yeah, you have a question? This is HG minus 25,000. Here? Oh, yeah. There you go. Thank you. Oh, I realized that I handed back the quiz and I didn't give you the key to it or tell you the answers. Most people did really very well on the quiz. Leonardo da Vinci was the ornithopter. He developed ornithopters, drew, studied birds, and designed airplanes. Montgolfier brothers, balloons. Daniel Bernoulli, fluid flow laws. Sir George Cayley, he was the first AE, set forth the first design of the airplane. Dwayne Wallace, Cessna after the Depression. or during the Depression. Otto Lilienthal, he was the guy that flew the gliders. Orville and Wilbur Wright, we've already talked about them, the first powered sustained flight. Bill Lear founded Learjet, which is one of the first jet airplane companies. Osborne Reynolds, fluid flow and friction. We'll actually talk about Reynolds number later on in the semester. And then Lloyd Stearman, Stearman Aircraft Company, and in fact, Stearman Field up near Benton, Kansas is named after that airplane that he built. All right. So we're having a quiz on Monday. You guys turned in your homework today. We went over the homework so that you could spot check your answers on Wednesday. So that's done. So now look for the new homework set on the standard atmosphere. And I'm planning to have the quiz on that. So I guess that's quiz number 3 on next Friday. So that'll be in here. So that means on Wednesday we'll go over the homework. There's only 4 problems. This should be fairly quickly. I mean, it's not going to be sit down in 2 minutes, you're going to be done, but it doesn't take a long time to do this. And we have quiz 2 on Monday. Hopefully I haven't lost track of the numbers here. And I will be gone, so a graduate student will be giving that to you. And then he will also be showing a video after that about the X Prize competition. And the key feature there is one of our former students, our alumni, was the structures lead on the Starship airplane. So, all right, so the next thing we want to talk about is chapter 4, which is basic aerodynamics. So let's say we have a wing. I'm drawing it in 2 dimensions on the board, so this is also considered to be an airfoil. And it's moving through the air, so often we will look at it as if the air is flowing past the wing. And the wing is stationary, so it's like we're an observer sitting on the wing, seeing the air come. And out here we have a certain velocity of the air that we call V infinity, because it's way out in front. And then the pressure is atmospheric pressure, way out in front of the wing. And then as the flow goes around, the shape of the airfoil causes a higher pressure. So the pressure goes up from atmospheric here, and a lower pressure on the top surface compared to atmosphere. And it's that pressure difference that gives us lift. Of course, we have to design the shape right, and we have to angle the wing so that we get that pressure difference. So to be able to calculate the lift, we need to be able to calculate the pressure everywhere on the wing. So we need to be able to model the flow. So we're going to have a bunch of equations that have to do with flow coming from, say, point 1 out here in front over to, say, point 2 on top of the wing. And there will be equations that relate pressure, density, and temperature in the front and at another point along a streamline. To do those equations, it depends on what type of flow there is. Because some types of flow require a lot more complicated equations than other ones. And so that's what I'm going to talk about now. So probably the hardest type of flow is if there's friction. Meaning if you're real near the surface and the air molecules are bumping into the surface of the wing, hitting the roughness there, the flow is very complicated, mixes around, not nice and smooth. And so that region of flow is called viscous. And we'll need that if we want to calculate the drag of the airfoil. So this is flow very near a surface. It has molecules hitting the roughness. And the molecules that hit those bumps in the surface slow down. And then they hit other molecules and slow them down. So you get a region of flow very near the surface that's slowed down. Harder to calculate. And then you get flow a little further away. Flow without friction, and it's called inviscid flow versus viscous. And so once you get far away from the surface, the viscosity doesn't make as much difference. And then under this type of flow, there's two different categories that require different levels of calculation or computation. And the easiest one is low speed flow. This is velocity less than 0.3 times the speed of sound. And you say, why does sound matter? It's because pressure changes as the flow goes through, or what pressure waves or sound waves are. Sound waves are pressure waves, so sound waves are changes in pressure. So it makes sense then that if we have low speed flow, it's low relative to these sound waves that move as pressure waves. And then the opposite, of course, could be high speed. And here we have velocities greater than about 0.3 times the speed of sound. This stuff at the top, the low speed, is called incompressible. We'll talk more about that later, but it pretty much means that the density is approximately constant. So that makes things really easy. We don't have to worry about density, and then it turns out we don't have to worry about temperature, so all we care about is pressure and velocity. So this is easy stuff. So it's a good thing that the Wright brothers airplane flew at low speeds, because they had the ability to predict and calculate low speed flow. I guess it kind of makes sense. It costs more, it's harder to fly faster. And then this is called compressible flow. And then under this one, but I'm going to have to jump back up here because I'm out of room. Under compressible flow, we have velocities below the speed of sound, but greater than 0.3. And then we have velocities greater than the speed of sound, and this is called subsonic, because it's less than the speed of sound, and this is called supersonic. And then if you get really high speeds, it's sometimes called hypersonic. All right, questions so far? One of the key features of when you're doing aerodynamics or fluid flow is to say, well, do we have viscous or inviscid flow? Do we have low-speed flow or high-speed flow? Do we have subsonic or do we have supersonic flow? And then you pull the correct equations out for that type of flow. As long as this assumption is valid, use the incompressible flow equations because they're a lot easier. Okay, there's some basic scientific concepts that we use. So matter is neither created nor destroyed. This is called the conservation of mass. The second one is Newton's second law. And this is called conservation of momentum. And then the third thing that we'll use is conservation of energy. This first one, matter is neither created nor destroyed, conservation of mass, is sometimes called the continuity equation, although I tend to call it the conservation of mass equation. It means that the matter is continuous, it doesn't appear and disappear. So in fact, that's the very first flow equation that we derive, is the conservation of mass or the continuity equation. We have time to get started on that, and I think we'll be good. All right, so the way we derive this and we're going to do the simplest version of this. It's what's called 1D steady flow. One dimension means that density, temperature, pressure vary only in one dimension. So I'm going to draw a picture of that. It means flow, the temperature or density only changes when we go from here to here. And then the steady flow means it doesn't change with time. So it's steady. It's like the flow is always the same all the time. Okay, so here's the picture we need. Draw an oval that's an inlet to a duct. And we'll call this point 1. It has an area A1. The velocity coming in here is V1. The density is rho 1. The pressure is P1. The temperature is T1. And the flow is uniform everywhere going in because these variables don't change with this dimension. They only change with this dimension going through. All right, so now I'm going to have to erase this. So can I erase this little part here? Because I need to draw the rest of my pipe or my tube. We good? So let's say this thing changes area like this, to where the flow comes out the other side. And it's going to have a velocity. Pressure density. The area here obviously is bigger, right? So what do you think is going to happen to the flow? Is the velocity here going to be faster or slower than coming in? Slower. Intuitively you think that, right? Why is that? It's correct in this situation. Right. So to get a chunk of flow, I mean, let's say at a time delta t, obviously we can calculate this length, right? It's velocity times time. The flow in 1 second, say, goes from here to here, right? To get that same chunk through here, it's only got to go through a shorter distance because the volume of that chunk there is bigger because the area is bigger, right? And so that's, intuitively we're thinking conservation of mass. The same amount of mass going in has to come out because it's steady flow. It's not building up inside. So, John wrote that. So the mass going in one inside this thing here, so we're going to calculate the mass in here, is going to be the density times the volume, which is the length times the area. And in delta t seconds, this much distance goes through. The flow goes from there to there because it's just velocity times time. So now we've written the mass in the left side is rho 1, v1, a1, delta t. So now let's do the other side. So in that same delta t seconds, coming out the other end, it's going to be density rho 2, that length L2, and then the area A2 and L2 is V2 times time. That's how far it goes. And again, we can see our intuition was right because if this is going to be the same as this, then the velocity has to be less because the area is more. And in fact, we often like to write this as not delta mass in delta t as we write it in mass flow rate. So delta mass 1 over delta t is rho 1 v1 a1. And then the delta mass at the other end divided by delta t, rho 2 v2 a2. And if nothing builds up inside, those two have to be equal. And in the limit, we call this m1 dot. If the limit is delta t goes to 0, and so that's rho 1 v1 a1. And then this is m2 dot. So if we write it like that, we say the mass flow rate. Mass per unit time going in has to equal the mass per unit time going out. Obviously, if more is going in here than is coming out per unit time, then it's going to build up inside. And the steady flow assumption says there's no building up in time. So this kind of equation does not apply to, say, a pressure tank and a pump pumping air into the tank because the pressure in the tank is increasing with time. So that's a non-steady flow problem. All right, so this is our first fluid flow equation, the conservation of mass. And it says that the mass flow rate in to a tube of area 1 has to equal the mass flow rate out the other side of an area 2. And that applies to anywhere in a duct, as long as we know the area. So if you have a duct, it goes like this. If this is A1, and this is A2, or even anywhere in between, we can call this A3. The mass going through A1 has to equal the mass going through A3, has to equal the mass going through A2. So you can write this equation between any 2 points in the flow in a duct. So how does this apply to an airfoil? So we have air coming in here, and it goes around like this. That's a streamline. And we have air coming in like this, and that air goes around like that. So we have a little fluid element here we follow, and another little fluid element here that we follow. And we can apply that equation across here and across here, because the definition of a streamline is that flow doesn't go across the streamline by definition, because we follow this element and it goes this way, so that means everything in between has to go in between. So you can apply it in flow like that, as long as you know the streamlines and what they're doing as well. How are we doing on time? 13. All right, I think we'll stop here, but the next thing we're going to talk about is what's called incompressible and compressible, which are some of the words we use for low speed versus high speed flow. So it turns out if you're going at low speeds, you don't get enough velocity of the air to compress the air if it slows down. The density won't change very much. Whereas if you have really high speed flow and you slow it down, then the slowing process compresses the air and you get density changes. Look at this equation. If we say for incompressible flow, the density is about constant, then we can say this cancels that and our equation becomes even easier. But again, this low speed flow has to be valid for us to do that. So when you're using this equation, I always want you to write it with the density in there. And then if you make the low speed flow assumption, say low speed flow assumed, or I'm assuming low speed flow, and then cancel the densities out. Okay, so we'll start there next time. Any questions? How are classes going? Okay, not just this class, but you guys have other in-person classes, or are you mostly online? 50-50 or hybrid as in? Yeah, a lot of the classes are in classrooms that are not big enough to hold the entire class. We're lucky in that I grabbed that lab over there and we've got a small class, so you're welcome to come every day in person. You're not required to be here. I think in person is better, and so as long as that works for you, you're welcome to come. I'm providing the Zoom in case something happens and you have to quarantine or you have to be at home for whatever reason. But I mean, personally, I think maybe most people do. The in-person is more engaging. So Not required, but I encourage you to be here as much as you can because I think it makes you more successful. Compared to other semesters, would you say this is a harder semester because of all this? Yeah, by what, a factor of 2 or? That makes a difference, yeah. Yeah, that's for sure. I don't think it's easy for anybody. As I've said before, stay safe. Do the best you can to make WSU a safe place so we can keep coming in person. All right, we're done for today. Have a good weekend. My student will see you on Monday, and I will see you again on Wednesday. Is Bruno Borges here? Is it Borges or Borges? There's that assignment you asked me to look at.